So, we had derived the fictitious forces or pseudo forces in rotating frame of reference, and two pseudo forces we found. One was minus 2 m omega cross v, which we called Coriolis force, and then the other was minus m omega cross r, that was centrifugal force. This omega is the angular velocity of the frame. This is important, of the frame, not of the particle, of the frame with respect to an inertial frame of reference. So, that is this omega, and then there is the position vector of the particle. This is velocity of the particle, everything measured from the rotating frame. This r, this v, acceleration, whatever, everything is measured from the rotating frame of reference. So, these are the things. Now, this centrifugal force, this depends only on the position and not on the velocity, and this depends on the velocity. So, if the velocity of the particle is 0 in the rotating frame, then you do not need to consider this Coriolis force, and only centrifugal force you have to work. We have assumed that omega is not changing with time. If that changes with time, we will have yet another term involving that d omega dt. Okay. So, if velocity of the particle is 0 in the rotating frame, then I need not consider this Coriolis force, and the only pseudo force is the centrifugal force, and that is what we generally encounter in school physics. Like when we say sun earth system, I talked about it earlier, sun earth system, and we assume that the sun is very heavy, and therefore, it is always fixed at one point. Of course, sun is not a point, is a very big object, but whenever you have a spherical body, spherically symmetric in density, that can be replaced for this gravitational forces by a single particle at its center. Okay. So, our sun earth system, we have worked extensively with this in the previous chapter, central forces. Even if you consider the finite mass of the sun, this two body problem can be reduced to one body problem, and you can always assume that the center of force is fixed in inertial frame, and this orbit is almost circular. The eccentricity is very small, and so if you assume this circular orbit, often question is asked, if sun is attracting the earth, why the earth does not fall? Why does the earth not fall into the sun? Okay. So, why it is not falling on the earth in the sun if the sun is attracting it in this fashion? That is a very general question which is asked in interviews and other things. Now, if you want to answer from the rotating frame, that means you make a frame where the axes are rotating. You can put your earth on the x axis if you so like, and as time passes in the inertial frame, this earth is moving and this frame is also rotating. So, if I use that rotating frame, then the earth is not moving, earth is at rest. That sentence I would like to emphasize. So, if you are using rotating frame, if you are using this frame which is rotating, if you are using rotating frame, your grammar should be correct, and you say that the earth is at rest, the earth is at rest, not falling, not falling into the sun. Because the force of attraction or the gravitational force is balanced by the centrifugal force. Correct explanation. Since I am using rotating frame of reference, I have to use a pseudo force, and since the earth is not moving in that rotating frame, earth is at rest. Therefore, I do not have to consider Coriolis force, the only pseudo force is centrifugal force, and that centrifugal force m omega cross r, which turns out to be m omega square r, that and this g m by r square. These are two forces, one force is this way, another force is this way, and these two forces balance each other. The resultant force is 0, so resultant acceleration is 0, and if it is not moving, it will not move. So, it will just stay there. This is the correct sentence. But if you want to use this earth frame or inertial frame, if you want to use inertial frame, same origin, but now the axes are not rotating. So, in this frame the earth is going in a circle, it is not falling, and there your explanation is different. Your explanation is that the force of attraction creates an acceleration towards the center, towards the sun. So, your explanation is the force creates an acceleration, force does not create velocity, force creates acceleration, force brings out change in velocity, and that acceleration must be in the direction of the force. So, although force is towards the center, acceleration is towards the center, but velocity need not be towards the center. No one says that velocity should be parallel to the force, resultant force. No, acceleration should be parallel to the resultant force. So, this creates an acceleration towards the sun, and that acceleration with initial velocity of the earth ensures that earth goes in a circle. So, this explanation is also correct. If you are using that inertial frame where axes are not rotating together with earth, then you say that earth is going in a circle, and that means there is a radial acceleration, and that means okay, that is perfectly all right. This attraction force creates that acceleration, and since the acceleration is towards the center, and therefore it bends to create that acceleration, to have that acceleration, and it goes in a circle, does not fall. On the other hand, also you can think that you remember the radial acceleration is r double dot and minus r theta dot square. Okay. So, r double dot is rate of change of r dot, and if initially r dot is 0, r has some value, r dot is 0, r double dot is also 0. So, that r is maintained. Okay. If r is fixed, r is constant, that means r dot is 0 and r double dot is 0, but that does not mean that ar is 0. If the distance from the origin is not changing, if the radial distance is not changing, radial velocity is 0. Velocity, you remember, velocity, radial velocity is just r dot, because the velocity vector was r dot r cap plus r theta dot theta cap. So, that radial velocity is just r dot. So, if r is constant, r dot is 0, there is no radial velocity, there is no radial this r double dot, that does not mean that the radial acceleration is 0, because this term is also there. So, if you have theta dot, if the theta is changing, then you can have acceleration without r double dot. So, we had done some problems on this also. So, these are the things that you must remember. The generally I hear the answers that since centrifugal force balances the centripetal force, therefore, the earth continues in the circle and does not fall into the sun. That grammar is wrong. Okay. Since I am writing this wrong statement, since the gravitational force is balanced by the centrifugal force, the particle continues in the circle and does not fall. In the sun. This is not acceptable. If we are using the rotating frame, then only you are using centrifugal force. If you are using rotating frame, the earth is not going into circular path, the earth is stationary, and that is why this statement is wrong. If you are saying that earth goes in a circular path, that means you are using that non-rotating inertial frame. If you are using that, then do not talk of centrifugal force. If you are talking of centrifugal force, you are using rotating frame, then do not say that it is going in a circle. So, these two things cannot go together, this statement is wrong. So, these are some of the things which one should remember when using the centrifugal force. The centrifugal force you have to apply on the particle is the mass times acceleration of the particle, which contains that force aside contains that centrifugal force. So, it is applied on the particle, but then it depends on the frame, which frame you are using, and from that axis of rotation of that frame, how much is the distance of the particle, whether the particle moves, does not move, goes in a circle or whatever. Okay. So, let me do a problem and we will have some practice on this rotating frame of reference and centrifugal force. So, here is the question: a horizontal circular disc is made to rotate about its axis with a constant angular velocity omega in the vertically upward direction. So, the disc is horizontal and therefore, the axis is vertical and omega vector is in vertically upward direction. So, if I see from the top, it will go anti-clockwise. So, that is this figure drawn here. This is the disc and this is horizontal plane and it is going anti-clockwise if I am seeing from the top. A straight groove is made along a radius. This is a groove. is a groove cut in this disc, and a small block is placed gently in the groove at a distance b from the center. So, at a distance b from the center, rotating disc, remember, and we gently place a small block here. Find the relation between the distance moved in the groove and the time elapsed. So, that is the question. So, we are using this disc frame which is rotating, and therefore, we are not given anything about friction and any other thing. Weight will be balanced by the vertical reaction force, contact force from the disc. So, the only force which is in the direction of motion is centrifugal force. So, we have centrifugal force, and that centrifugal force, I can call it x axis, I can call it x axis here, y axis here, and z axis along the vertically upward direction, which is also the direction of omega. So, the centrifugal force, which is minus m omega cross r, you can work out. If the particle is somewhere here at a distance x from here, then this is minus m, omega is omega k cap, this is omega, cross this omega is omega k cap, cross this r is x I cap, right. At a time t, it has already covered a distance x, and so the r vector is x I cap, and this will be equal to minus m and then omega and omega. So, omega square and this x, and then these cross products, cross k cross j. So, I j k, k cross I, k cross I, k cross I will be j. So, this will be j, and then k cross j is minus I cap. So, it is minus r, this is minus I cap. So, it is m omega square x I cap, right. So, we have told it several times that is the distance from the origin m omega square times the distance from the axis, that is the magnitude of centrifugal force, and it is away from the axis, right. So, that is centrifugal force. You do have a velocity. This particle is not at rest with respect to this circle, this disc, this rotating disc. On the disc, it is going in the groove. We are using the disc frame, and therefore, our x axis, y axis, z axis rotating about the z axis in the inertial frame, but in this disc frame also this particle is moving in the groove. So, velocity is not 0. So, we have to also look for the Coriolis force, right. Coriolis force is minus 2 m omega cross v, which is minus 2 m, omega is omega k cap, and cross v, v is in x direction. So, it will be v I cap, which will be equal to k cross I is j. So, it is minus 2 m, then omega v, and then k cross I is j. So, it is j. So, you have Coriolis force. Coriolis force is not 0, and that is in minus j cap direction. That means, that is in the minus y direction, negative y direction. But in the negative y direction, there is no motion because of the groove walls, and hence you have yet another force by the wall. This Coriolis force, this is the centrifugal force, this is 1, this is the Coriolis force, this is 2. Remember, this is horizontal, I am drawing everything in the horizontal plane. So, this is your centrifugal force, this is centrifugal, and this is Coriolis force, So, if this groove was not there, then it would have picked up velocity in y direction. Okay. But now, since the groove is there, the wall will exert a force, a normal contact force N, and that force will balance this Coriolis force. So, ultimately it is motion only under the centrifugal force, right. So, although the Coriolis force is there, but then this N, the normal force, that normal force is by the groove. Balances the Coriolis force. And so, your equation of motion is m omega square x, this is the force in x direction, motion is also in this direction, this is equal to m d2x dt square. So, d2x dt square is equal to omega square x. Okay. Had it been minus omega square x, the solution would have been that simple harmonic type, but it is plus. You can still make it of that type, minus here, I omega here, whole square here, and x. Call this quantity as some omega prime, which is complex, which is imaginary, and you have the equation d2x dt square is equal to minus omega prime square and x, and you know the solution. The solution is x is equal to a, and then I can write it this way, e to the power I x plus b e to the power minus I x, my t, I omega prime t here and I omega prime t here. This is x. If you write in cos sign, you can do that. This quantity is cos of omega prime t and plus I times sine of omega prime t, and similarly this quantity is cos of omega prime t and plus sine of omega prime t. So, you can write into it in the familiar cos omega prime t and sine omega prime t also. The constants will be correspondingly added. If you are writing cos omega prime t, you will have a and then plus b and so on and so on. So, the constants can be adjusted, and you can do this. So, this expression cosine type or exponential type, both are equivalent, only these constants will change, they are anyway arbitrary and they will be decided by the initial conditions. So, it is this, and here in our case it will be e to the power I, then omega prime is I omega, and this t here, and then plus b, this e here, then minus I here, and this omega prime is I omega here, and then t here, and this is e to the power minus omega t and plus b into e to the power plus omega t. So, this is how x and t are related, and now a and b are two arbitrary constants to be decided by the initial condition. So, what happens at t equal to 0? What happens at t equal to 0? At t equal to 0, the particle is at a distance b. So, x is equal to b. So, x is equal to b equal to a and plus b, because when you put t equal to 0, this quantity is 1 and this quantity is also 1. So, it is a plus b is equal to b, and the other initial condition is that we had put it gently. So, although it is moving and we place it, we have not given any x velocity to start with. So, x dot is 0, dx dt is 0, and from here if you write that x dot or dx dt or velocity of the particle, that will be omega b e power omega t I am differentiating with respect to time. So, omega and then b and then e to the power omega t, and from here it is minus and this omega minus omega and then this capital A and e to the power minus omega t. This is the velocity at time t, and at t equal to 0 the velocity should be 0, and therefore, 0 should be equal to omega b, t is 0. So, this quantity is 1 and minus omega a, this quantity is 1. So, this is it. So, b is equal to a, omega times b minus omega times a is 0, it tells me a and b are same, and here the sum of these two is b, and therefore, I know that a is equal to b and is equal to b by 2. So, place it here and you get that your answer. When x is equal to, what is a? A is b by 2, e to the power, and what is this? Yes, here, put it here. So, a, this is b by 2 and then e to the power minus omega t plus capital B is also small b by 2 and then e to the power omega t. So, that is it. This is b by 2 and then e to the power omega t and plus e to the power minus omega t. This is called cos hyperbolic, e to the power omega t plus e to the power minus omega t divided by 2, that is called cos hyperbolic function of this omega t. So, you can write this as b cos hyperbolic of omega t. So, you can do a plot and see how that x changes with time and so on and so forth. So, we will continue with more problems related to rotating disk.